This video includes the first 2 hours of a course I am currently putting together called JavaScript for Visual Learners, and this content represents about 70% of the first part of the course. If you would want to get the entire first part of the course free of charge, you need to head to 3dcodeworld.teachable.com, where in addition to more video tutorials, you would get access to the interactive code snippets that come as a companion to every lesson. The link to the course page on the Teachable platform is provided in the description below. You would find that this course is different from most JavaScript courses out there. For one thing, the course is excellent for visual learners, and it is packed full of 2D models, 3D models, and animations. Something else that would never happen in this course would be you watching me code. I just don't believe that this is a good way to learn, and I have completely avoided doing that. Instead, the lectures would focus on theory, where we would be taking apart many code examples, but most of the coding would be done by you, using the interactive code snippets that were mentioned previously. This is why I highly recommend that you actually experience this course on the Teachable platform and not on YouTube. Please enjoy this free portion of the course, and make sure to support the channel by subscribing. And now, let's begin. So why should you be taking this course, and what has been the underlying objective for putting together this course? Simply put, the focus is on understanding and on building knowledge from the ground up. In all honesty, a lot of courses out there try to go a bit too fast, and in doing so they end up skipping a lot of information, and this ends up holding you back. Let me give you an example of what I mean when I say presenting information from the ground up. For example, one of the most basic things we can have in a program is the notion of a value. So we should really understand what a value is before we go ahead and try to understand what a variable is, or how variables are named. To really understand what variables are, we have to at least discuss a little bit computer memory. And it would only be at this stage when we would be ready to start discussing both primitive and object value types in JavaScript. And it should only be now when we start discussing things such as what is a string value type, or what are string literals and how we can define them, or what are objects and what are object properties and methods, or how we can devise visual models so that we get better intuition about what objects look like and how their methods get called. I think that you get the idea. When you start from the ground up, you really understand how things work in the background, and you become a better programmer. Your programs would have less bugs. Now, of course, starting from the ground up does not mean that we would be skipping the hard part of the language. Sure, we would try to use simple models as much as we can to illustrate simple concepts. For example, we can easily visualize the addition operator in JavaScript as something that requires 2 operands to return a value. But this would not stop us to discuss, for example, how memory allocation might work when we declare a variable, or how we can encode characters in binary so that we can understand how the string value type works a lot better, or to fully understand how the number value type in JavaScript works in the background, which is something that even many people that have been doing JavaScript for a while do not fully comprehend. At times we will be going real deeply and discussing things such as, for example, what is an abstract syntax tree and how it relates to our source code. And we would even be taking peeks inside the ECMAScript specification, which is where browser makers get their information from about how JavaScript should behave. There is something else about the course that you may have noticed. The video component of the course is very visual, and it is intentionally so. I firmly believe that using visual metaphors, and metaphors from real life for that matter, is an excellent way of teaching the more complicated parts of JavaScript. And you can really say that I went all out on that one. You can almost think of this course as an art project. It is packed full of 2D diagrams, 3D diagrams. There is actually a reason why I called this project 3D Code World. The course is also full of animations which should help you understand things better. For example, when we look at code, we would often take it apart to make sure that we really understand what happens at every step. So we have plenty of 2D and 3D models, as well as animations, which makes this course excellent for people who like to learn visually. There is a reason why this course is called JavaScript for Visual Learners. So if you want to think of objectives, you can think of this course as attempting to give you a very good foundational knowledge of the JavaScript language, where we would try to cover most things that are important, and we would use many visual examples to make sure that the most complicated and frequently confused parts of the language are in fact understood. Hopefully you would enjoy the journey of learning one of the most popular languages on the planet and the language of the internet. Let us say a few words about the various topics we would cover in this course and what would be discussed in every section. All sections would be fairly visual with a large number of 3D models and animations and careful code snippet breakdowns. Altogether, the content of the course contains over 2000 slides, so there would be a lot of ground to cover. This course is in fact split up in 4 parts, and you can almost think of it as 4 courses into one. The first part introduces JavaScript and has various sections such as an overview of the language, history of the language, with most of the focus on understanding what are primitive data types and object data types. We would in fact go quite deeply in these subjects and really try to understand them, because these subjects are quite fundamental to almost anything that follows. The second part of the course will focus on understanding expressions and statements in JavaScript. These are again fundamental things that we would not be taking lightly. We will be covering these topics in a fair bit of detail because they are so important for understanding our programs, for understanding how everything works under the hood. The third part of the course will be covering functions and classes. We are really going into the deep here because these are some of the more complicated parts of JavaScript. Here we will be discussing topics such as scope, closures, execution contacts, what happens on the stack during function calls, and nested function calls. And then topics such as prototypal inheritance, constructor functions, and then classes. This section would contain a large number of visuals that would help you understand these fairly complicated and involved topics. The last part of the course would deal with more advanced topics, things such as modules and asynchronous JavaScript. We would discuss and understand the event loop, callbacks, promises, and recent additions to the language such as async await. One principle that we would follow would be the complete separation between watching video tutorials and practicing coding. This is something which is not followed by most courses out there. It seems to me that the vast majority of courses on the internet mostly consist of an instructor doing coding and you following along. But I don't think that that's a good idea. I don't think that that teaches you all that much. I think that a much better way to formulate a course is to have videos that emphasize the theory and then having exercises where you do your own practice. The nice thing about the video platform that we are using is that we can easily do that. We can have a video and then immediately underneath it we can have interactive examples which you can actually run and play with on the same page. To do this, we would use an embedded version of a RunKit notebook, which is like a JavaScript sandbox that can be embedded on a website. What this means in practice is that code snippets can not only be run, but can be changed. They can be something that you can play with and experiment with, and this is a great way to learn. This is a great thing because what it means is that we can use videos to emphasize how and why things work in JavaScript, and then we can use the code snippets to get practice in what we just learned. The video tutorials do of course contain code, but this is code that we are free to take apart, so that we fully understand what happens when the code is run and what happens under the hood. While we are on the subject, can we say just a few words about what is likely the best way to learn how to code? Learning programming is a very weird exercise because on the one hand there is just so much to learn, and on the other there is so much information out there. And in fact you would likely never run out of things that you don't know, that you don't understand, and that you might even feel slightly stupid about. The imposter syndrome is a very real thing in programming. Just do a Google search on that. If this is a mountain that you would want to climb, you might need to be strategic to get there. One thing that you will have to do is to figure out a way to get interested and to stay interested in coding. And this would be different for different people. Some people might enjoy putting together games, for example, or working on their own website, or contributing to open source projects. Some people even enjoy nerding out on the language design itself. What is important is that you pick something that gets you excited, because learning how to code can be frustrating at times. And in this way you will not quit midway. The next thing that you just have to understand and accept is that learning how to code involves a lot of practice on your own. This is why I don't like code-along tutorials. They seem to be emphasizing the wrong thing. The last thing that is always a good idea is to be getting a solid language foundation. This means learning some of the boring stuff, learning the theory, learning how everything works under the hood. At least some of the journey would involve a lot of alone time and dealing with your own struggles, building personal projects, becoming an expert Googler, and getting a learner mentality, because there is just so much to learn. At least part of your journey should also involve hitting the book. You have to understand how programs work. You have to understand how JavaScript works under the hood. You have to clear up any areas of confusion, and there will be many of these. So if we want to go back to what we were discussing previously, it would be the video tutorials that will be covering the subjects on the right hand side. And then it will be the interactive exercises and self-practice that is focusing on the stuff on the left hand side. We really don't want to be mixing the two. Of course, you should be taking everything that I just said with a grain of salt. We all learn in different ways, but keep in mind that the path you're on is not easy and many people quit. So I do feel that if you find what gets you excited about programming, and then if you learn to deal with the struggle that comes along the way, and then if you get good foundational knowledge, your chance of success would be greatly amplified. What are the key characteristics of JavaScript? If you want to look at the language from a bird's eye view, looking at the forest rather than the individual trees, we can think of JavaScript as the de facto language of the web. This is probably the thing that makes JavaScript the most special. If you're doing almost anything web-based, it would not be long before you would realize that this is a language that you would have to learn and you would have to master. From its inception, JavaScript has been designed as a language which should be fairly easy to learn for a non-programmer, which has determined a lot of its design choices. For example, JavaScript is dynamically typed. Now, what do we mean when we say that a language is dynamically typed? What we mean is that we are only checking types. For example, is something a number, is something a string, at runtime, one line at a time when that code is in fact run. This is in contrast with statically typed languages, where we check types before we ever run the program. JavaScript is also weakly typed. When we say weakly typed, what we mean is that JavaScript would often be making changes of types for us, which is called type coercion, which would allow us to do things such as add a string to a number and then end up getting a string without the program complaining that we are mixing types. Many languages do not allow that. Most modern implementations of JavaScript are also what is called just-in-time compiled. Now, what do we mean by that? When you take the source code of a program and then you try to convert it to machine code, there are two basic ways of doing that. One of them is using a compiler, where you would take the entire code before the code is actually run. You would check for types and errors and things like that, and you would very often optimize it. And then you would run the code. An alternative approach to this is to use an interpreter. And in this case, what you would do is the computer would be converting each line of code sequentially into machine code. So the code would be run line by line when all of things such as type checks would be done at this stage, at runtime. When I try to think of concepts such as compiled or interpreted, I always like to use analogies. So, for example, imagine that you are organizing a trip for a head of state, let's say a president, that has to visit 5 cities. Very often this type of trip would be compiled. What do I mean by that? there would be a plan ahead of time. Somebody would check and double check the plan, make sure that everything would work, make sure that all of the streets would be open at that time. And this is what a compiled program tends to do. It does a lot of checking before we actually run the trip, before we run the code. You can think of an interpreted program, on the other hand, like going on a road trip with your friends, where you still plan to visit the same 5 cities, but you sort of check for errors at runtime. For example, you might discover that there is no train going from city A to city B. So what then is just-in-time compilation? Well, you can think of it as having the best of both worlds. You still run the code line by line, but then you keep looking ahead for improved efficiencies. It is like getting to a train station, seeing that there is a large queue of people there, and before you even line up, getting on your phone and starting to check if there is some alternative way to get to the next city, alternative transportation. To go back to real code, think about, for example, a loop that calls a function many times. Initially we would call the function the interpreted way, and we would go through every single line of code in it. But soon the JavaScript engine would notice that we keep calling the same function again, and it might find an optimized way to get the result back. This would be an example of just-in-time compilation. Now, what I just did was give you a very high-level overview of some fairly complicated concept. Dynamically typed, weakly typed, just-in-time compiled. I don't expect you to fully understand what these things are now, but the point is to get you at least acquainted with these concepts, and maybe you can read more about them later, when the time comes. This is one thing that you would find you would have to do all the time when you're learning to program. You would get acquainted with something and then you would revisit it many times until you fully understand it. Something else that you have to be aware of when you first start learning JavaScript is that JavaScript is referred to by more than one name. Sometimes we refer it to as JavaScript or JS, but sometimes we refer it to something called ECMAScript or ES. Now there is a whole lecture which goes into that topic, so I don't want to be spending too much time on this now. But the idea is that ECMAScript is a standardization body. JavaScript is in fact a standardized language. So very often when we talk about the standardized version of JavaScript, we would be referring to it as ECMAScript. For example, when browsers put together their JavaScript implementations, they will be consulting the ECMAScript specification so that they all follow the same behavior. Each browser writes their own implementation, so it is important that we have some consensus about what a browser is supposed to do with a web page. There is one peculiarity about web languages which makes them a bit different from, for example, compiled languages. If we update the language in any way, we have to make sure that code written previously on older websites still continues to run. You can imagine that there would be a big problem if every time the language specification changes, all of the websites that used JavaScript before that stop working properly. So the point is that JavaScript has to be backward compatible. We can improve the language, but we always have to make sure that the previous decisions that were made there are still active. The old code still works. Now, as I've mentioned before, I always like to think of metaphors and analogies when I try to learn something. I was thinking of a good way of explaining backward compatibility in something that is a bit more intuitive than language design itself, and I came up with the following. Imagine that you wanted to escape the city, so you build a nice little house in a beautiful nature spot. There you can spend time doing one of your favorite things, which is to ride your horse around your property. Times change and the city you tried to escape from is growing. All of a sudden people want to move in the area, and then you decide to become a developer and to build a building. But remember, unlike real life, everything has to be backward compatible. So you build the building, but you keep the foundations of the house, and the horse, and the trees. You build a staircase, and then you build a pool. But the building that you built did not have an elevator, so now you need to have an elevator. It turns out that the people really want one. So you can move things around, but you still have to keep everything that was there before, the pool and the staircase. It turns out that some real wealthy people want to live in the area, so you decide to build a helicopter pad. But it also needs an elevator, so to build the elevator now you have to cover up the pool. So all is great, you have a beautiful apartment complex. But its internal design has been affected by all of the choices that were made previously. Remember, we started with a simple house. For example, our building now really has 2 elevators. And it also has a horse that you can ride around your property in. It's all still there. The evolution of JavaScript has in fact followed a similar theme. Design choices that were there initially are with us to this day. Yet the first versions of JavaScript were for a simple scripting language. Nobody was thinking that we would be building complicated applications using JavaScript. The plan was to in fact do this using Java. But history turned out to be different. JavaScript not only became the de facto language of the web on the front end, but is increasingly being used on the back end. And it has in fact built a huge ecosystem of libraries and frameworks. JavaScript is not going anywhere. The increased use of JavaScript for sophisticated web applications has also greatly affected its design in recent versions. JavaScript has in fact now transitioned into a fully capable general-purpose programming language. Competition between browsers has also resulted in JavaScript engines which are incredibly fast. All of this has been great for the language and for its adoption, but unfortunately some of the issues with backward compatibility remain. JavaScript is no longer that easy to learn. It has ballooned into a fairly big language, and yet we still have to be aware of older implementations. And then we have the huge ecosystem we talked about. Especially on the front end, people are finding all of the things that they have to learn and master a bit overwhelming. But remember, many of these tools are still based on JavaScript. So getting a good, solid, foundational understanding of the language would end up being a big time saver in the long run. This video would go over the history and evolution of JavaScript. Having some understanding about how the language came to be is fairly important because it allows us to understand why many of the features of the language that are currently available are there and how they came about. Even though the story of JavaScript begins in 1995, we should really start the story 5 years earlier, when at CERN, the European Organization for Nuclear Research, a fellow called Tim Berners-Lee devised the technologies behind the World Wide Web. In 1993, the web became an open standard, and a number of browsers quickly came about, the most prominent of which was the Mosaic web browser. The Mosaic web browser was devised by Mark Andreessen and Eric Bina. This is the same Mark Andreessen that a year later would form a company called Netscape that you may have heard of, and is currently one of the most prominent venture capitalists in Silicon Valley. The Mozilla web browser is really the browser that popularized the internet. It was really the first internet browser that could show images on a page in line with text rather than showing them in a separate window. In 1994, Netscape Communications Corp gets incorporated, and also in the same year, the first version of their browser, Netscape Navigator, becomes available. Netscape Navigator is another major improvement over the existing technology. What the browser allows is the display of text and pages while a page is loading, which is a big change from what was available previously, where a page had to be fully loaded before it can be shown. And remember, at the time, internet speeds were quite slow. Notice how quickly things are moving. In 4 or 5 short years, we have gone from the creation of the concepts behind the World Wide Web to having venture-backed companies which are creating browsers and having wide adoptions. The world has discovered the internet. Just think about the following. Netscape gets formed in the early part of 1994, and in mid-1995, only a year later, it has an IPO which shook the world. All of a sudden, the company is valued at over $2 billion. This is the first company in history to do that so quickly. And this is in fact what started the internet boom of the late 90s. 1995 is also the year when Microsoft discovered the internet. Bill Gates has a famous internal memo called the Internet Tidal Wave, in which he basically says that the Internet is the future of the company and they should devote full resources to it. The first version of Internet Explorer 1, becomes available this year. This is the beginning of what is known as the browser wars, when Microsoft and Netscape battle things out in terms of browser domination. Microsoft is packaging their Internet Explorer browser free of charge with their Windows 95 product. It was in fact these practices that led to a major antitrust case against Microsoft, which it lost, where it was declared a monopoly. The reason why I'm telling you all of this is because this is the background against which JavaScript came to be. The first version of JavaScript was famously designed in only 10 days at Netscape by Brendan Eich, soon after their IPO. It was first incorporated in Netscape Navigator 2. And what it allowed was to add a dynamic element to the browser. You can think of browsers before JavaScript as simply document viewers. You send a request to the server, you get back an HTML page, you display it. Why is JavaScript called JavaScript? Well, as with the rest of the story, nothing is simple. The first working name for JavaScript inside Netscape was Mocha. A second name was then LiveScript. All of this was happening while a deal was brewing between Netscape and Sun Microsystems, who at the same time was heavily advertising and about to release a new language called Java. The idea was that Java would be the main language of the web for developing sophisticated applications, and then JavaScript would be a glue language for non-programmers. Many design decisions of early JavaScript had a lot to do with keeping the language as simple as possible. This is why JavaScript is called JavaScript. The initial plan was for it to be a companion language to Java, which would be a lot easier to learn. This is also why the syntax of JavaScript is very similar to the one of Java and to other C family languages. You should be aware that many of the similarities between JavaScript and Java are only superficial. And in fact, on the inside, the object model that JavaScript uses is quite different, and so is the inheritance model that it uses. So Netscape now has a language which it can integrate with a browser and make web pages dynamic. The language is called JavaScript. Microsoft quickly responds. It reverse engineers the JavaScript language, incorporates it in its engine, and it calls it JScript. JScript is added to Internet Explorer 3 in August of '96. Again, things are quite quickly moving. There is a new problem that needs to be resolved now. We have two browsers, all of which have a very similar but not identical implementation of a dynamic language, while we have users who want web pages displayed correctly on all browsers. This is how the next phase of JavaScript development came to be: standardization. It would be very convenient if there is an external body that makes decisions about the JavaScript language, which then browsers would simply implement. The standardization organization picked was the European Computer Manufacturers Association, ECMA, today known as ECMA International. Future development of JavaScript would now be made by committee, with the initial members of the committee including Netscape, Microsoft, Sun Microsystems, and a few other companies. The first organizing meeting took place in November of 1996. A first draft of a standard was soon afterwards prepared, which was accepted by the ECMA General Assembly in June of '97. What would the new language specification be called? It turns out that the name JavaScript was trademarked by Sun Microsystems and they were not willing to give it up, so a temporary name was picked. The language specification was called ECMAScript. Well, guess what? It is called ECMAScript to this day. It is a horrible name, but it's here to stay. So JavaScript has many names. Most people in the community call it JavaScript, but typically when we are referring to something that has to do with the specification, we would use the name ECMAScript, or an abbreviated version of it called ES. So in September of 1997, the first version of ECMAScript was published with official name of ECMA Standard ECMA 262. The following year saw the second edition of the standard, which largely addressed some issues with the first edition, with most of the important changes to the language happening in the third edition. It would in fact be the third edition of the standard that would be the de facto standard of JavaScript for over a decade. The third edition of the standard incorporated the major additions to both the Netscape and the Internet Explorer browsers up until that point, in addition to a few other changes. Quite a few things were added at this stage that many users of JavaScript would recognize. We're talking about things such as the switch statement, do statement, object and array literals, the strict equality operator, quite a few array methods such as push, pop, shift, concat and slice, as well as exception handling, among many others. A chapter was closed with ECMAScript 3 and the committee was ready to open a new chapter, where JavaScript can become a much more powerful language. Unfortunately, things did not quite go as planned. At this stage, the browser war between Microsoft and Netscape was pretty much over, with Microsoft being declared the clear winner. This resulted in both companies somewhat losing interest in rapid innovation of their browser products. Netscape was acquired by AOL, which ultimately led to the discontinuation of their browser, while Microsoft acquired over 90% market share of the browser market by 2001. By this time, Microsoft was working on its own internal technologies and lost interest in developing an open web-based language standard. But the web and use of JavaScript continued to grow, which led to the committee to reconvene and continue working on the next version of ECMAScript. But after a couple of years of work of a new, very ambitious version of JavaScript, a major split in the committee formed. Some of the members of the committee felt that the changes suggested were way too ambitious and would break a significant portion of the existing web. They favored a more gradual improvement of the language, which is backward compatible, with changes that do not require new syntax. This in fact resulted in the committee splitting up into groups, one of them working on an improvement of the older version 3 of ECMAScript, which was informally called version 3.1, and the other one continuing work on the new and updated version of the language, ECMAScript 4. The inability of the ECMAScript 4 group to ultimately deliver a working specification in time led to the decision for version 4 to be abandoned and for version 3.1, which was now renamed ECMAScript 5, to be adopted as the next specification. ECMAScript 5 gave us important new features such as strict mode, getters and setters, improvements in security such as the ability to freeze objects. Even though abandoned after a decade of effort, not all work done on ECMAScript 4 was going to go to waste. Many of the features planned for this phase would in fact make it to the next version of the specification, ECMAScript 6. Work on ECMAScript 6 went a lot more smoothly with consensus of the committee. The new version of the specification was accepted in 2015. As with all things JavaScript, names abound. This version of the specification is commonly known as ECMAScript 6 or ES6 or alternatively as ECMAScript 2015. The new naming scheme of ECMAScript followed by the year of publication has in fact been adopted since, with all new versions following this format. ES6 was in fact a major update, and it has turned JavaScript into a powerful general-purpose programming language. It gave us block scope declarations with the let and the const keywords. It introduced classes for the first time in the language, as well as modules and arrow functions. Things such as promises, iterators, spread and rest operators, among many others. Since 2015, the committee has committed to an annual specification schedule. There is also a new approval process which consists of 5 stages. Stage 0 consists of an initial idea, while Stage 1 involves a formal proposal. Stage 2 involves an initial draft of the proposed change for the specification, while Stage 3 should have a version that is almost final, ready for final feedback from the community. The last stage of the process is Stage 4, which means that the proposal is ready to be included in the next version of the specification. We covered a lot of ground in this video. I think that apart from making an interesting story, I do feel that getting a feeling for how the language came to be in its present-day state when you're trying to learn it is fairly important. The truth is that as you're learning the language, you would frequently come across names such as JavaScript, ECMAScript, ES3, ES6, and those things do have to have meaning for you because they are important. There is a lot of legacy code out there. Many websites are written in the older ES3 format, while many websites would be written in the ES6 format. And I do feel that you have to be familiar with both, as you would undoubtedly come across examples that use one or the other. I wanted us to start at almost the simplest place we could start with, which is the notion of a value. So what is a value? A value is a piece of data, such as a number or a string, or pretty much any entity which can be accepted by JavaScript, which can be manipulated by a program. So we are talking about a very simple concept here. And what we very commonly use for it in this course, in terms of a metaphor, is a ball. You can imagine a ball is like an indivisible object. And in this case, a ball can be almost anything. It can be a number, such as a number 7. It can be a string, such as hello world. It can be a boolean, something like true or false. Don't worry about what those things mean specifically. We will be discussing them at length later on in the course. It can be something called undefined, or it even can be an object like a function. For example, if we have the number 40, which is a numeric literal, 40 can be a value, but we can also have a decimal number. We can have a string, for example, John is a valid value. We can have something like true or false. Both of these are valid. Or we can even have something like null, which is the null literal, which is used when we want to represent when there is no value for that specific variable that we are interested in. So even null, even nothing, is a specific and acceptable value for JavaScript. The next thing that we have to be aware of is that values can be used in a couple of different ways. We can either use them immediately, for example, as part of a calculation that we are making, or we can store them for later use in another place in the program where we would retrieve them back. So if we think of a temporary value, we can just think of a ball which is about to be used. Or if we think about a value being stored in memory, we can think about moving that ball into a shelf and then using it later on when we would actually need it. So the value is stored in computer memory. So in this case, we have the ball, which is the value, and then the shelf itself represents an address in memory, a place which we would name so that we can get the needed value as it is required. Let us say a few words about how values are actually stored in computer memory. What we want to do is we want to build a more robust mental model of what happens inside of the computer when we run a program. A very useful way to think about memory is to think of a number of boxes which are placed adjacent to one another, with each box obtaining a specific address, a specific number that refers to it. Now each box in this case would represent 1 byte. Now you have heard this term before. And then each byte in turn would represent 8 bits. Now the bits are the zeros and ones which are so famous in computer science. So the idea is that by using such structure, we can actually place values using bits in bite-sized chunks, and then we can use the addresses of these bytes to always find a value in memory. So if we, for example, have some human readable code, let num1 equals sign 40. Let is a keyword. Num1 in this case is an identifier for a variable. The equal sign is the assignment operator in JavaScript, and then 40 is a value. So what we're doing in this case is we are defining a num1 variable, and then we are placing the value 40 in it. But what would happen in machine readable code? Well, in order for us to actually do follow the instruction, the first thing that we have to do is we have to find an empty slot in memory. For example, address 5 is empty. We will then allocate 48 bits or 8 bytes, so 8 boxes, so that we store a number. Now in JavaScript, it takes 8 boxes, 8 bytes to store a number. This is just the convention that the language uses. So we allocate 8 boxes and then we store the number in memory. How do we store the number in memory? By putting 48 zeros in one in a specific order, which means something to the computer, so that we can retrieve this value if we go to address 5. So notice we have defined a value, we have associated with an address. So if we want to retrieve this value from memory, all we need to do is we need to go to the correct address and then retrieve the value. So note that our num1 identifier that we used in our human readable code was in fact not needed anymore. So as far as the computer is concerned, it can completely do everything that it needs to do by only looking at the address and then the chunk of memory associated with it so that it can retrieve a value. So let us get a better intuition of how we manipulate values in memory. Let's go back to our previous human readable example where we defined a num1 variable and then we assigned the number 40 to it. Again, visually we can quite easily represent this by defining a shelf num1, then generating a temporary value and moving it to that location. So now we have a num1 variable with the number 40 at that location. Now, what if we have a second line of code though, where we take the same variable num1, but now we want to assign a new value to it, 41. How can we represent this? So if you look at the little arrow which appeared on the screen, we actually changed a single bit in this 64-bit series of numbers. So now at address 5 in computer memory, we have a new value which corresponds to the numerical value 41. How can we represent this visually using our balls and shelves metaphors? Well, this would be the same as generating a number 41 and then placing it at the same location over the previous value 40 at the num1 shelf. So notice the previous value at num1 has been removed. It has been replaced by the new value. There is no way of getting it back anymore. What would happen if we add a third line of code where we now define a new variable num2 and in it we would place the num1 value, which is 41, added to the number 40. How can we represent this? Once again, we would run this line of code. Well, what we would do is we would go to a new address in memory at place 13, which is empty, and then we would put in a series of zeros and ones there that correspond to the number 81 in this case. Let us see this visual again using our shelves and balls. What would happen now is we would define a new shelf, num2. We would then add up the value at the num1 shelf to the number 40. To do this, we would use an addition operator. So both of these values would go into it. The addition operator would add them up and it would give us the result, which is 81, which would be placed at the num2 variable. So notice what happened here. We didn't remove the value from the num1 variable, so we still have a ball with 41, with a value of 41 there, but now we have defined a new shelf, a new variable, a new address in memory which has a new value, 81, which we can also keep using in the program. So let us say a few more words about what exactly is a variable and how is it different from a value. To make programs useful, we have to be able to store values in memory. These values can be numbers, they can be strings, they can be booleans. And then we have to be able to access them back and get them at some stage in the future. And this is where variables come in. These values would be associated with names of variables, which we can then use to retrieve them as they're needed. So there is this direct relationship between a name of a variable that we use, shown here on the left-hand side, and a value shown on the right-hand side. Notice that there is some terminology here. So sometimes we would refer to this name component as a name, sometimes we would refer to it as a label, sometimes we would refer to it as an identifier. The value tends to be called a value. But notice that there is a relationship between a place in memory which we are labeling by assigning it a name, and then the value which would tend to go there. So in human readable code, if we have something like let num1 equals to 40, num1 would be the variable in this case, so num1 would be the name that we would use to refer to the value which would be stored at that location. And then 40 would be the value which would be stored and associated with that variable. We also have to remember that in machine code, things are different. We don't use names to refer to memory locations. We use simply addresses. So we use numbers, which refer to a given location in memory. And then the value itself would be represented by a given numbers of zeros and ones, depending on the value type. So we do have to be aware that there is an association between the name given in our human readable code and an address in memory. There is a direct relationship between them. And in fact, as far as the machine code is concerned, these names are not even there. They're only using the addresses to do what they need to do. And then the value in our human readable code, for example, of the number 40, and the space in memory associated with that address, the zeros and ones which would occupy the definition of that value in memory. So how do we declare variables in JavaScript? We have a couple of ways of doing it. We can use a let keyword or we can use a var keyword. We would only be focusing on the let keyword for now to keep things simple. But before we start talking about syntax, let us again make sure that we fully understand what a variable is. So on the right hand side, we have a shelf, a space in memory. We have labeled that shelf, so we have a name which is identifying that space in memory. We have a value, and then we place that value at that shelf location. So now we have a value and we have a way of getting it, finding it, and retrieving it if it's needed. But the key thing about a variable is that every time we define a variable, for example with the let keyword, we are in fact allowed to change values of that variable. So if we were to, for example, introduce a yellow ball and place it at the same location, it is going to replace the red ball. That is in fact allowed. If we are to introduce a green ball, it would be allowed to replace the yellow ball. So notice that we can recycle the same location in memory and add different values there, with each new value successively removing and replacing what was there before. Now this will be contrasted with something called a constant, which we will be discussing in just a little bit, which doesn't allow to do that. So if we use a constant, once we define a constant, we are no longer allowed to change it. But let us keep to variables now. So the main ways in this course in which we will be defining variables, we will be using the let keyword. So in this case, we have the let keyword, followed by an identifier, num1 in this case, followed by an assignment operator, followed by a value, the numerical value 40, followed by a semicolon. This is the most typical way of defining a variable in JavaScript. This is one of the most simplest programs you can in fact write. So what you've done in this case is you have identified a name which you would use as a variable. You have assigned a value to it, the value 40, and then you have something which you can retrieve later. If we want to make things a bit more general, we have a let keyword followed by an identifier, followed by an assignment operator, followed by a value. Technically, instead of value, you can substitute an expression at that location. So all expressions result in a value. We are not talking about expressions just yet, so let us just for now, for simplicity's sake, just think of a simple value which goes on top of a shelf. Now I did mention that there is another way of defining values using the var keyword, so we can have a var identifier assignment operator value. We will be discussing this a bit later on in the course, just for simplicity's sake, but be aware that there is a second way of defining variables in JavaScript. Now that we discussed what variables are, let us discuss what a constant is. As we did previously, before we go into syntax, let us visually understand what a constant does and how it is different from a variable. Now in this case, we have already defined the variable that we defined in the previous example. So we have something called variable name, which is the name that we have given to a shelf which has a particular value on it. Now what we will do now is we will define a second shelf, a second place in memory. This time around we will define this shelf as a constant. So we would use the name const name to refer to it. And what we can do now is we can also place a value at that location. Now this step is identical to what we were doing before with the variable names. But here comes the change. If we use a constant, we are not allowed to make changes to that value after the first assignment. You can think of this as placing a cage around that ball. So we have defined a value which refers to that particular location, but we are not allowed to make changes anymore to it. So in fact, if we try to assign a new value to constant name, we would get an error. We are not allowed to do that. So if we want to define variables, we would use the let and the var keyword. But if we want to define a constant, we would use the const keyword. So a constant address can be assigned a value only once. That is kind of the idea. In terms of syntax, the syntax is very similar to what we were doing with let and with var. We have a const keyword followed by an identifier, followed by an assignment operator, followed by a value. As I mentioned before, there can also be an expression at this location which evaluates to a value. So far we have discussed what a value is, the fact that values can be stored in variables or constants in computer memory, but we have not yet discussed what types of values we can in fact store in memory. We have seen a few examples with numbers, but there is a lot more there. And this is what will be discussed in this section. So what types of values can be stored in variables and constants? The key thing here is types. It turns out that we can store different data types at a given address in memory. What are some examples of different data types that JavaScript can accept? We can talk about numbers. Or we can talk about strings, such as text stored in a value. We can talk about booleans, things such as true or false. Or empty values, things such as undefined, or something not shown here, null. Or we can talk about objects. Functions in JavaScript, for example, are objects, and they're in fact first-class values. We can pass them around like that ball visual metaphor we have been using. We have spent a fair bit of time discussing the relationship between a name, such as an identifier, and a value, and then how all of this gets converted to an address in memory, and then a series of bits which are stored, which is where the value is kept in memory. So if we have some human readable code, let num1 equal to 40, in this case we are assigning both a name and a value to a variable. And all of this can be thought of as an address in memory and then bits of code stored there. But what types of values can we in fact store in memory? We have to be very precise about this because JavaScript has to know how to store them, how many bytes of data, for example, they should allocate for a given value type. The different value types have different requirements in fact. So the types of values that we can have in JavaScript, We have 7 types of values which are called primitives or belong to the primitive data types, such as number, string, boolean, null or undefined, and a couple of specialized data types which are a bit more advanced in terms of usage, symbol and BigInt. So all of these data types are primitives. And alternatively, we can also store objects, and many things in JavaScript will be objects. We can have our own custom objects, we can have arrays which are objects, we can have functions which are objects, we have quite a few of those things available to us. What are primitive data types in JavaScript? They are types of values which we can store in memory, which tend to be simple, and for the most part they will be all value types we can save which are not objects. We're talking about things such as strings, numbers, booleans. We do have to be aware though that 5 of the 7 types of primitive data types that are available in the language can have wrapper objects which can be very quickly built by JavaScript to make them behave like objects. So almost everything in JavaScript can behave like an object. What are the examples of primitive types that we have in the language? We have the number type with a number of varieties that we will be discussing. We have the string. We have the boolean. We have a couple of types that represent either something which has not yet been assigned a value or an empty value, which would be null and undefined. And then we have a couple of specialized types of primitive data types, the symbol and the BigInt. We also have to be aware that we have the other alternative. All of the value types which are not primitives would be objects, and there would be many subtypes of these, such as functions, regular objects that we will be discussing a bit later on in the course. Let us view a few examples of primitive data types. For example, if we have the following line of code, let num1 equal to 40. 40 in this case would be of the number type, which is a primitive. If we have const num2 equal to 3.14, 3.14 would also be of the number type. So both of these examples are of the number primitive type. Notice that the number primitive type can assign both integers and fractions. So JavaScript would use a single value type to represent both of these types of numbers. We can also have strings defined as variables or constants. We can also have booleans defined. We have 2 possible values for a boolean. It is either true or it is false. And then we have these empty values, null and undefined. The specialized types are symbol and BigInt, in this case, placed in the sim1 variable and the bignum variable. In all cases, when we define a primitive value in memory, it would go at a given address location, and it can be placed both in a variable or it can be associated with a constant. It is important to realize that once we assign a primitive value using a constant, it cannot be changed anymore. It would be set in memory. This would not be true for assigning variables. In quite a few places, when we would be discussing code execution in JavaScript, we would be using a visual metaphor of a room which represents either global or function scope. And inside the room there would be a table which we would be referring to as a workbench table. And on it we have specialized machines which give us the primitive data type. So we have one for null, one for undefined, one for number, one for string, one for boolean. Again, these specialized types, symbol and BigInt, are not included here just for visual reasons, but you can imagine that they would also be there. The first primitive data type that we would discuss would be the string. You can think of a string as a series of characters which are held together in a single value in memory. For example, if we have the following code, let string1 equals John in quotation marks. John in this case would be the value, a string value, and it would also be a string literal. Now a string literal is simply a source code representation of a string. We can define string literals in a couple of ways. We can use double quotation marks, or we can use single quotes. Both of these are acceptable ways of defining a string value as far as JavaScript is concerned. Now, let us say a few more words about strings in JavaScript. Let us give a few more details. Each character in a string would be preserved in 16 bits of data in memory. Characters in a string would be preserved sequentially. Each character would be represented using the Unicode standard, where a character gets converted into a number, which then gets input in memory. And the inputting part in memory also involves an encoding, and the encoding that we will be using in JavaScript will be UTF-16. Let us spend some time trying to understand a bit better character encoding in JavaScript. As we've mentioned before, a string is a sequence of characters. So if we have the name John, it would be represented by 4 characters, which are sequentially preserved in memory. But as far as the computer is concerned, what computers really like to work with are binary numbers. So computers are very efficient at dealing with numbers, and they don't really have a way of specifically dealing with strings and with characters. Which is why we actually have to take our initial characters, which make up the string, and somehow convert them into another storage type in memory. To do this, we have to in fact go through a couple of steps, which involve a convention. A convention in this case is a way of doing something so that everybody agrees on what the initial input is and what the output would be. And the first convention would have to be how to convert characters into numbers so that each character that we use ends up being converted to the same number. And then the second convention would be how to in fact encode these numbers into bits and bytes. For example, in the first step, we very often use the Unicode standard. The Unicode standard currently has over 140,000 characters as a part of it. And in the second step, we very often use different standards, but the UTF-8 standard is quite widely used across the internet. UTF-16 is in fact the standard which is internally used inside JavaScript. Let us go through an example. Imagine that we have our old string, John, and we will then use the Unicode standard to see how we can represent the 4 characters in John and convert them into specific numbers which we can then use. Now on the right hand side we see what is named as the ASCII standard. So this is a node standard for relating characters to numbers. The Unicode standard uses exactly the same numbers right at the beginning of its definitions. So the first 127 characters in Unicode are the same as the ASCII characters. So let us see how we can represent the name John in both ASCII and Unicode. Well, what we will do in this case is we need to find the letters. So we have capital J, we have small letter O, H and N, and as we can see, all of these letters correspond to a number. So the letter J would correspond to 74, O would correspond to 111, H would correspond to 104, and then N would correspond to 110. So notice all the standard is doing is assign characters to numbers. We would be making an additional step to convert a character number to encoded bits and bytes in memory. We have all agreed on a way in which we can use the same standard, the Unicode standard, to represent a character as a number. Let us now discuss the next step that we need to do, which is to agree on a way in which we can convert a number into strings of bits and bytes that can be recorded in computer memory. To do this, we will start off with the simplest possible scenario where we deal with numbers which can be described in a single byte, so in 8 bits of data. We would use our old examples where we use the name John. We converted it to numbers 74, 111, 104, and 110. And we will specifically focus on the first character in this case, capital J, which corresponds to the number 74 based on the Unicode standard. So the next thing that we need to do is figure out a way of how can we record this number 74 into something that uses only bits, zeros and ones. And to do this, we would use binary data. And more specifically, binary data which is recorded based on this UTF-8 standard. Well, a long time ago, people figured out a way that you can efficiently describe decimal numbers into binaries by taking numbers with base 2 and raising them to different powers. So for example, if you take 2 to the power of 0, this would be equivalent to 1. If you take 2 to the power of 1, this would be equivalent to 2. If you take 2 to the power of 2, this would be equivalent to 4. 2 to the power of 3 would be equivalent to 8. 2 to the power of 4 would be equivalent to 16. You get the drift. 2 to the power of 5 would be equivalent to 32. And 2 to the power of 6 would be equivalent to 64. So it turns out that one way of describing the decimal number 74 in binary is to figure out which of these numbers you can use so that if you add them up, you end up with 74. One thing you may have noticed is that we never use the very first bit of the 8 bits which are available to us on the left. Well, it turns out that this bit is reserved. It always contains 0 if we are describing a character by a single byte of data. One thing that we would learn a bit later on is that using the UTF-8 standard, we can describe characters by multiple bytes of data if this is required. And we would often be using these initial bits on the left-hand side so that we tell the computer that we are talking about linked bytes which should be looked at together. To understand how decimal numbers fit into binary data, one metaphor that I like thinking about is how we can fill a hole by different sizes of rectangles. In this case, we have rectangles which correspond in width to 74, 32, 16, 8, 4, 2, and 1. So one thing that we can envision is how can we in fact infill the hole which is found below, which is 74 units wide by these rectangles. So what we can do is we can check whether a given rectangle fits in the hole. If it does, we keep it there. If it doesn't, we don't. So the 64 rectangle did, so we would put in 1 in its place. We would then try the same with 32, which doesn't fit. We would put in 0. We will try the same with 16. It doesn't fit again. We would again put in 0. We will try it again the same with 8. It does fit, so in this case we put in 1 again. We try it with 4. It doesn't fit. We put in what? 0. We try 2. It does fit. We put in 1. And 1 in this case, because we have already infilled the hole, would contain 0. So this is very similar to what we will be doing with binary numbers when we want to represent a decimal number. Now let us view the same thing viewed in the standard way. In this case, we have a number of empty boxes which we will be filling up with zeros and ones, trying to figure out how to represent the number 72. So we will do something very similar. We will start off with the question is, starting from the left, is 64 less than 74? Yes, it is. So we will put in 1. We will then ask ourselves, is 32 plus 64 greater than 74? If it is, we will put in 0. We will do the same with 16. So is 64 plus 16 greater than 74? It is again a greater number, so we would again put in 0. Is 64 plus 8 greater than 74? In this case, it is not, so we would put in a 1. So we keep doing this, and we end up getting the needed binary notation. So if you're interested in a binary number, this is how you get it. So the number 10011010 corresponds to the decimal number 74. So notice the letter J was represented by this stream of 7 binary numbers with that 0 in front of it. So this is 1 byte of data. So we can think of the letter J corresponding to these numbers. So all we need to do now to describe the entire string, the name John, is to do the same for the other characters. Now it turns out that all of these characters would be defined quite nicely into a single byte of data. So in all cases, what we are doing is we are recording these streams of zeros and ones, putting them together, which would give us an entire string, ending up with the entire name John. So it turns out that there is a limit of how many characters we can in fact encode in a single byte of data. And the limit is quite straightforward. All we need to do is we need to use a binary number where all numbers are ones, which in this case would give us an addition of all of the corresponding decimal numbers for a total of 127 possible scenarios. Well, this 127 character set is in fact what the initial ASCII standard was based on, where we had some initial instructions, numbers, Latin characters, commonly used characters, and this was all that was available to us. But you can imagine that there is a need for us to describe a lot more characters, different alphabets, etc. So this is why the UTF standard has been widely adopted. It involves a very elegant way of describing almost an unlimited number of characters by making the individual bytes communicate with one another. How do we do that? Well, it turns out that if you want to use more than one byte of data, all you can do is to start each byte with a predefined set of numbers. For example, the first byte will start with 110, and the second byte will start with 10, and this will tell the computer that those two bytes are in fact linked. Now, what we then do is we would use the empty unused bytes to start recording our binary numbers. And in this case, we have 11 of these available to us. So we can use 2 to the 0, to the power of 1, 2 to the power of 2, etc. We will jump to the second byte because the two bytes are again linked. So we will have 2 to the power of 6 already belonging in the other byte, getting us all the way up to 2 to the power of 10. So in this case, we have 11 different bits available to us, making the whole possible set of characters a lot bigger. And in fact, we have 2047 of these. So we have 2047 possible characters we can encode with 2 bytes, which is very neat. But again, the real world actually involves a lot more alphabets and emojis and things like that. So we can very easily go to 3 bytes if we like to. In this case, we go all the way up to 2 to the power of 15 for a total of over 65,000 possible characters. Or if we go to an encoding with 4 bytes, we can go to over 1 million possible characters. So notice that in all cases, all we are doing is we have a standard notation where the first byte contains a number of ones followed by a 0, which is telling us how many bytes of data we are following. So the number of ones is telling us how many bytes would go together, and each successive byte would start off with 10. This is very neat because even if we end up starting at a random location inside of a stream of bytes, as long as we see a 1 and a 0 in the beginning of a byte, we would know that we are in the middle of a character, and all we need to do then is go back to the beginning and we can piece everything together so that we can start understanding how the encoding works, which is very powerful. Let us go through a 2-byte encoding example of the Greek small letter sigma. So the Greek small letter sigma, in terms of a decimal number in the Unicode standard, is represented by the number 963. So how can we represent 963 using 2 bytes of data? As we previously discussed, both of these 2 bytes of data would have some bits right in the beginning of them, which are telling us that we are dealing with 2 linked bytes of data. As we also discussed, we would be using the remainder of the empty bits to describe the number. So if we want to describe 963, all we need to do is to figure out which of these decimal numbers corresponding to 2 to different powers add up to this number, which is quite straightforward to do, as we have previously discussed, giving us the following solution. So in this case, we would have a 0, we would have 4 ones in the first byte. In the second byte, we would have 4 zeros followed by 2 ones. So this is all we need to do. Let us spend some time trying to understand the hexadecimal notation, which is quite commonly used when we are describing bits and bytes. We have already seen how decimal numbers can be related to characters. For example, for the Greek small letter sigma being represented by the number 963, and how these numbers can be represented based on the UTF-8 encoding in a couple of bytes. But it turns out that it is fairly difficult for us to deal with so many numbers in a row. So what we very often do is splitting this up into series of 4, i.e. chunking them, where we need to describe each combination of bits within each chunk by a single character, by a single number, which becomes very useful for our human brains to deal with these long streams of zeros and ones. Now, let us convince ourselves that there are in fact a limited number of possible combinations of zeros and ones within 4 bits. And in fact, there is 16 possible combinations. If you look at the first two numbers on the top left, where the first two numbers are 0 and 0, and then look at the second pair of numbers, you should convince yourself that there is actually only 4 different possibilities there. We can have 0 and 0, 0 and 1, 1 and 0, or 1 and 1. If we do the same thing with the first two numbers being 0 and 1, and then the first two numbers being 1 and 0, and then the first two numbers being 1 and 1, we end up with 16 possible combinations. Now, let us see how we can describe these combinations using what we are more familiar with, which is the decimal notation. Well, one thing that we can very easily do is we can just use the numbers from 0 to 15 to describe all possible combinations. So if we will take our 2 bytes of data representing the Greek small letter sigma, what we can quite easily do is we can represent the first chunk by the number 12, the second chunk by the number 15, the third chunk by the number 8, and the fourth chunk by the number 3. This is in fact completely valid, but there is an issue here. There is a bit of a problem because both the numbers 12 and 15 are internally made up by 2 numbers, so all of a sudden we have to worry about differentiating 1, 2 from 12. And it turns out that there is a much more elegant solution here. We can use the hexadecimal notation. And the way the hexadecimal notation works is we use numbers with base 16, so we end up having 16 different possible numbers, not only 10 as is the case for the decimal notation. We once again use specific notation to represent these. We in fact use the same numbers as the decimal notation for the first 10 possibilities. And then we use letters from the beginning of the alphabet, starting from the letter A and ending at the letter F, to describe the combinations that correspond to 10, 11, 12, 13, 14, and 15. The reason why this is very neat is because we only need to worry about a single character, a single number representing 4 bits of data. So if we look at the same series of data, we can quite easily represent it, for example, by the number C for the first 4 bits, 1, 1, 0, 0, by the number F for the next 4 bits, 1, 1, 1, 1, by the number 8, where the bits are 1, 0, 0, 0, and by the number 3, where the bits are 0, 0, 1, 1. Notice this is very neat. We've described this entire long series of bits and bytes by only 4 characters. This is very powerful. This is very useful. One place where you're likely to encounter hexadecimal notation is in fact when we are describing the Unicode standard. Quite common Unicode characters are represented by hexadecimal numbers. This is just a bit more convenient. It is a bit shorter to describe. Now, before we get to hexadecimal numbers though, let us spend just a minute describing how decimal numbers are described. So if we take the Greek small letter sigma, as we've already described, it corresponds to the number 963. Let us actually understand what 963 actually represents, because this would be very useful for us to understand how hexadecimal numbers work. The notation 963 can actually be represented by 3 times 10 to the power of 0, which is 1. So 3 times 1, which is equal to the number 3, plus the 6 corresponds to 6 times 10 to the power of 1, which is 10 of course, so we end up getting the number 60. And the 9 corresponds to 9 times 10 to the power of 2, which is 100, which corresponds to 900. So in fact, the decimal number notation includes all of this information. It's just a shortcut for it. And this is exactly what we do with hexadecimal numbers as well. So the hexadecimal equivalent for the Greek small letter sigma, if you look up the Unicode standard, is U plus and then 03C3. Now the U and the plus, this is just part of the Unicode notation, so we don't need to worry about that. But the important bit is what comes afterwards. This is a hexadecimal number, which we can read exactly the same way as we dealt with the decimal number, but now we will be using base 16 instead of base 10. So we can represent the 3 as 3 times 16 to the power of 0, which is equal to 3, plus the number c, which corresponds to 12 times 16 to the power of 1, which ends up being 192, plus the number 3, which corresponds to 3 times 16 to the power of 2, which ends up being equal to 768, plus 0 times 16 to the power of 3, which of course is 0. So if you add up these numbers, you once again get 963. So this is how hexadecimal numbers work. They're very useful because 16 is quite easily related to binary data at base 2. Let us now discuss the number data type in JavaScript. Apart from regular numbers that we are used to, the number data type does include additional types such as positive or negative infinity, or even something called not a number. Now, if we will start off with a line of code where we place the number 40 inside of a variable, let num1 equal to 40. 40 in this case would be a value, and this value would be of the number type. Considering that this is source code, we can also refer to the 40 as a numeric literal. If we want to dig just a little bit deeper and try to understand a bit better what happens when we enter a value 40 and assign it to a variable, what would happen is that there would be an address in memory, and then 8 bytes of data would be allocated so that we can save this number. Now, 8 bytes of data means that to save the number 40 in binary, we would be allocating 64 bits of data. Now, we can define integers such as 40 using the number type in JavaScript, but we can also define fractions. So for example, if we have the number 3.14, the number 3.14 would again go in 8 bytes of memory, which would consist of 64 bits of data. And once again, we would have something that looks very similar to what we did with the integer 40. So notice that we are storing both integers and fractions in exactly the same way in JavaScript, in the same data type. So if we want to summarize the key characteristics of the number type in JavaScript, we can say that it is stored in 8 bytes in memory. Its type is double precision 64-bit format, which is used in a number of languages for their double type. JavaScript did not invent its own standard. In fact, it uses something called the IEEE 754 standard, which again is used in quite a few languages for the double type. And the same type of number is used, for example, in Java or C# in addition to other numeric types. So what is interesting in JavaScript is that we are mostly using one data type to describe everything. And we are using this data type to describe both integers and fractional values. It is very important for us to get a very good feeling for what exactly gets stored once we input a number. If we add a third line of code, const num3 equals to 3.14, the number here represents the first 100 digits from the number pi. And then if we would call back num3 and show us the value that was stored, we would see a much smaller number. So what is going on here? Well, it turns out that there is a way in JavaScript to in fact force JavaScript to give us more digits. We can use the number built-in object, which has a method which is called toPrecision, where we can tell JavaScript how many digits we want shown. So in this case, we tell JavaScript, okay, show us 100 digits. This is how many digits we in fact put in our initial number. We do that, and then we see that the numbers have changed. We have the numbers right at the beginning, which are shown in yellow, which correspond to what was initially input. And these were in fact the numbers that JavaScript gave back to us without defining the precision. We then have the numbers in blue, which are apparently different from what we just put in. And then we end up with a whole lot of numbers in green, which are all zeros. So what is going on here? Make sure to see the continuation of the video, which would be going over all of these details so that you get a better feeling for what's going on. But the main thing to be aware of for now is that JavaScript would often assign numbers, store numbers as approximations of what we put in. And this is especially true if we put in very big numbers or numbers with a lot of digits. We can summarize numbers in JavaScript in the following way. We can talk about finite numbers, which are typically the numbers you think of when you think of numbers. Right in the middle of them, you would have 0. Now a caveat here is that you can have both a positive 0 and a negative 0. This is something that the standard that JavaScript uses allows. Outside of this range, we would have positive infinity and negative infinity. Now it's important for us to understand that infinity here is not mathematical infinity. All it refers to is numbers that are bigger than the acceptable range of the number values as defined by the bytes that we allocate in memory for a number to be stored. And the limits of those things are quite specific. For example, if we use one of the built-in objects in JavaScript, the math object, and use its power methods, its pow method, what we can do is we can figure out what is the value of 2 to the power of 1023, and we get a very large number. But if we were to find out what is the value of 2 to the power of 1024, we hit infinity. So notice there is a sharp boundary here. Another data type, which is probably the most confusing one in JavaScript, is the not a number one. And to find out more about this, again, make sure you watch the video until the end, because we will be covering all of those topics in a fair bit of detail. As with many things JavaScript, to really understand numbers, you have to peek under the hood. You have to understand what is happening in the background, how are numbers in fact stored. Now, a key thing to keep in mind is that for us to store a numeric value, we only have 8 bytes available to us, which means 64 bits. So if you think about 8 bytes as 8 boxes, and then each byte containing 8 internal bits to it, 8 additional boxes, altogether we would have a total of 64 bits available to us. And in these 64 bits, what we need done is to store both integers or fractions, very large numbers and very small numbers. This is actually quite a tricky thing to do, and the solution here is quite elegant, as you will find out. So for us to handle all of this, we in fact separate the series of 64 bits into 3 components. We have one bit which represents the sign, whether something is positive or negative. We then have 11 bits which represent an exponent. All of this would make a lot of sense in just a little bit. And then we have something called the significant, which is also known as a mantissa or a coefficient, which is where we will be storing most of the digits that would represent the number. So if we think about base 2, and again remember that all of these numbers are stored in binary, base 2 would be raised to a given exponent, which will be defined in the 11 bits corresponding to the exponent. And then this whole number will be multiplied by the significant, which is a normalized binary number where we would have most of the digits which are involved. And in addition to that, all of this would be multiplied by the sign. So if the number is negative, the sign there would indicate a negative number. This is very similar to scientific notation of decimal numbers. So for example, if we have a number such as minus 3.455554 times 10 to the power of 15. This is scientific notation. We will be doing something very similar, but for binary data. Let us now look at the components in a bit more detail, starting off with the sign. So if we have 0 for the sign bit, it means that the number would be positive. And if we have 1 for the sign bit, it means that the number would be negative. Things are as simple as that. Jumping to the exponent. Now, as we've already mentioned, the exponent has 11 bits available in it. And as you may remember, an 11-bit exponent basically means that we would be raising 2 to different powers, starting from 2 to the power of 0 to 2 to the power of 10. How many numbers can we play with here? Well, if we put in ones for all these bits, the biggest possible number would be 2047. So this is the possible range. So in a very simple world, we could have just raised 2 to the power of 2047, but this is not what in fact happens. There are a few complications here. First of all, if we add all ones, this is actually the number that is reserved for the number infinity. So we cannot use it. So in fact, we have one less number to play with. So the maximum here would be 1046. Notice that there is a 0 for the very first bit in this series. And the other main thing that we want to do is we want to be able to use this field to describe both very large and very small numbers. And we are about to do a very neat trick here. What if we move the 0 to the middle of this range, to the value of 1023, which would then give us the possibility to describe both positive and negative numbers using the same 11 bits of data. So the maximum number would be 1023, and then the smallest possible number would be minus 1023. 1023 would correspond to 2046, and negative 1023 would correspond to 0. So notice that we've done a very neat trick here. So in fact, we can, by the same 11 bits of data, we can describe a number as big as 2 to the power of 1023 or as small as 2 to the power of minus 1023. Remember, having a minus in the exponent means a lot of zeros after the decimal, so a very small number. Now, we have already talked about how there is a limit between finite numbers and infinity. Well, this thing is real. So for example, if we would raise 2 to the power of 1023, we would get a very large number. We have seen that before. And if we raise 2 to the power of 1024, we get infinity. So any numbers bigger than that would give us infinity. Notice this is the hard limit, and the reason why it is there is because we have 11 bits available to us for the exponent part of the number. So what about the significant? Well, what the significant represents is a normalized binary number. That means a binary number which is in the format of 1 point something, zeros and ones. Now, to understand normalized numbers, let us start off with a decimal example. So if we have the number 111, you can think of it as having a decimal point immediately after it. So it is like having 111 and then a decimal point. So for us to go to this scientific notation, to a normalized number, what we need to do is we need to move the decimal point a couple of spots to the left, which means that we are also multiplying the number by 100 or to 10 to the power of 2. So this is how scientific numbers work. Well, we will do exactly the same thing with 111 as a binary number. So remember, to have 111 as a binary, we would represent the number by a series of ones and zeros. And it turns out that the series of numbers that adds up to 111 is 1101111. So this is a number. Again, we can imagine that there is a decimal point immediately after it. So how can we normalize the number? Well, we have to move the decimal point to the left, actually 6 times. So the normalized version of 111 in binary would be 1.101111, which is raised to 2 to the power of 6. So if we want to represent the entire number, we would have, this is a positive number, so the sign would be 0. the significant would be 1.101111, and then we would multiply the entire thing to 2 to the power of 6. Now we have to represent the 6 also in terms of binary. But remember what we need to do. We would not just convert 6 to binary, but we would first add 1023 to it, because we are dealing with this biased exponent. So for us to get 6 plus 1023 is 1029, and the numbers that represent 1029 are shown in red below. So if you look on the top left, the ones that we need to put in the exponent are the following. So we need to put one right on the left of the exponent and then 2 more ones towards the right hand side. So this is the exponent that is needed. What about the normalized portion of the significant? Well, we will do another little trick here, because all binary normalized numbers would start with 1 point something. It turns out that we don't in fact need to save the 1 point in our binary number, because we are trying to preserve as many bits as possible. So you can think of having 1 point in the gap between the exponent portion of the number and the significant portion of the number. So the numbers that we would actually record would be the bits after the decimal points, which in this case would be 1 followed by a 0 and then 4 ones. Now that we understand how numbers are stored in memory in JavaScript, we are ready to understand what the different types of numbers that are allowed are. For example, if we have the number 0, all a 0 is a number which has all 0 bits in the 11 bits of the exponent and all 0 bits in the 52 bits of the significant. Notice that there is no condition for the very first bit, and we do in fact allow a positive 0 and a negative 0 because of that. This might sound strange, but again, the designers of this system have decided that this is a useful thing to have in a language. So for example, if we would run the following code, 1 divided by -10, the answer is -0. On the other hand, if we compare positive 0 to a negative 0, the answer is true. Now this is not true for any other number, so -1 is not equal to 1, but the designers of the language in the ECMAScript specification, which is the specification of the language that browsers etc. are using, it is clearly stated that if we compare two numbers x and y, and if x is positive 0 and y is negative 0, the comparison should return true. If x is negative 0 and y is positive 0, again the comparison should return true. How do we deal with infinity? Well, to define infinity, we would add all ones in the 11 bits of the exponent and all zeros in the 52 bits of the significant. So this is the definition of infinity. Notice that the first bit is again free, so we can have positive infinity and negative infinity as we have discussed elsewhere. What is infinity? Well, anything greater than 2 to the power of 1023 would give us this number. And let us view a few examples. So if we have infinity and if we multiply it by a number, by a finite number, we would get infinity. If this number is negative, we would get negative infinity. If we take a number and if we define it by infinity, for example, dividing -10 by infinity, we actually get 0. But notice that the 0 here is a negative again. Now, again, we have to remember that infinity in JavaScript is not mathematical infinity. All it means is a big number, a number bigger than we can handle by the bits and bytes available in memory. So this is why it sort of makes sense that we start approaching 0. If we have -10 divided by 0, and this is a strange one, in mathematics we are not allowed to divide anything by 0, but again, because in JavaScript very often the numbers are approximations, the designers of the language have decided that the most reasonable thing for us to do is in fact to have this equal infinity. So if we have -10 divided by 0, this would give us -infinity. And again, those are a few things which we just have to be aware of and we have to know. And these things are in fact described again in this ECMAScript specification of the language, where it is clearly said that division of an infinity by 0 results in an infinity, division of an infinity by non-zero finite value results in a signed infinity, division of a finite value by an infinity results in 0. So all those things are actually given to us as rules that browsers have to follow. And in this case, we have another condition. Division of an infinity by infinity results in nan, not a number. So let us say a few words about this non-a number type of number, which is probably the most confusing one of the bunch. We have already discussed finite numbers, 0 and its positive and negative variety, positive and negative infinity. But there is one last type of number that usually people find the most confusing, which is the nan, the not a number type. Now you can think of the not a number type as a hack, and we tend to use it when we've done something wrong or we've done something illegal, for example dividing 0 by 0. Using none allows us to get this unexpected value but yet not stop the program from running and debug the problem later. So how do we define a not a number? We can have 0 or 1 for the sign, so both positive and negative would be allowed there. We would have all ones in the 11 bits of the exponent, just like the infinity numbers. But unlike the infinity numbers, which had all zeros in the significant, this time around we would have any number but all zeros. So even if we have a single one, the combination of bits on the screen would give us the not a number type. So let us view a few examples of not a number. For example, dividing 0 by 0 gives us not a number. Multiplying anything to a not a number gives us not a number. Adding, subtracting would lead back to the result of not a number. And even taking this to an extreme, not a number is in fact not equal to itself. And again, this is something that people find very strange. But again, if you think about debugging and think about the fact that not a number is something which is a value that we need to look at afterwards, this sort of makes sense. So not a number with triple equal not a number, strict equality gives us false. So this number is not equal to itself. We are now ready to understand safe integers. What do we mean by safe integers? Well, the number object in JavaScript has a property called maxSafeInteger. So if we run that, we get a decimal number. So it turns out that this is the biggest number that we can safely use in JavaScript. If we are interested in integers, i.e. whole numbers, anything bigger than that would result in some kind of rounding. Now, instead of having this memorized, let us understand what happens. This same number in terms of binary and in terms of binary exponent would give us the ones that we are currently seeing on the top left. Now these are the numbers that are resulting in these ones, which gives us the number 1075. Now if we subtract 1023 from 1075, we get 52. So this is actually the number represented in the exponent, which means that the exponent here is 2 to the power of 52. So notice the maximum integer number has nothing to do with us running out of exponent space. We can have a lot more exponents than 52. So if we do the rest of the number in bits, we would see what the problem is. Notice all ones. So in fact, the maximum integer number is the place where we run out of significant bits, right? So this is the biggest possible number we can include in a significant. Let us view a few examples. For example, if we take the maximum safe integer, the number which is seen above, and then if we add 1 to it, what we get seems to be reasonable. So the first number ended with 91, the second one ends with 92. That is fine. But notice what happens if we add 2 to that number. So we take the same number which ends in 91, we add 2 to it, and notice we again end something that ends with 92. Something has gone wrong. Notice we are already rounding. We've run out of numbers. And if you want to do even something more interesting and to compare the maximum safe number plus 1 to the maximum safe number plus 2, you actually get that the two numbers are equal. So we are taking the same number, we are adding 1 to it, and then we are adding 2 to it, and we are comparing the results, and we are getting that their two results are equal. And again, the reason for that is because we've gone into this unsafe territory where we've started rounding things. What happens if we take the maximum safe integer and add 4 to it? Again, the initial number ends with 91. If you add 4 to 91, you expect 95, but we in fact get 96. So notice what happens here. We've run out of space and we start rounding things. So these are things that we do have to be aware of. Something else which many people get confused are why simple decimal numbers give us strange results in JavaScript. And the reason for this is because sometimes simple decimal numbers do not make simple binary numbers. For example, if we have the number 1, which we can represent in binary as 1 times 2 to the power of 0, this is how we would describe this number using the bits notation. Notice this is quite straightforward. We just have a number of ones in the exponent and then everything else is 0. If we have 0.5, which is 1 divided by 2, in binary this would be 1 times 2 to the negative 1. We again have something straightforward where we have only ones in the exponent and then 0 in the significant. If we divide this number by 2 and end up getting 0.25 in decimal, in binary this would be equal to 1 times 2 to the power of negative 2. We again have a simple number to deal with. If we divide this number by 2 in turn, we would again get a simple number to deal with. So notice that binary numbers work very well as long as we are multiplying by 2 and dividing by 2. This is why they are binary. But what would happen if we have a simple decimal number, for example 0.3? How would 0.3 be represented in binary? The exponent would be straightforward. It would be the same exponent, in fact, 2 to the power of minus 2 as we had for 0.25. But notice what happens in the significant. We keep getting 2 zeros, 2 ones, 2 zeros, 2 ones. This is in fact a number which does not end. So if we need to represent this number in binary, we would run out of significant again. So we would be rounding things off. And the moment when we start rounding things off, we start getting strange numbers. So 0.3 would not be equal to 0.3, it would be an approximation of that number. So if we would run a line of code, for example, let num3 equal to 0.3, a decimal number, and then if we do the two precision game again, so that we give the result now with precision of 53 digits, this is what we get. So notice the real number that got converted to binary and then back to decimal is not 0.3 anymore, but it's 0.29 and then a whole lot of digits afterwards. And this is why one of the textbook's examples of why JavaScript is weird, which is why 0.1 plus 0.2 equals to 0.3, this gives false. Well, this sort of makes sense now. All of these numbers are approximations. They're not these nice numbers that work very well in binary. And because of that, if we add two of these and then compare them to a third one, they don't add up perfectly. You can imagine the number 0.299 etc. is not really equal to 0.3. So if we add a few of these numbers together, we would not end up getting exactly the same result. The next primary data type that we will talk about will be the boolean. This is probably the simplest data type to describe. All we have is two possible values. One of them is true, the other one is false. So if we have the following line of code, let bool1 equal to true. True would be the value, it would be of the boolean type, and it would be assigned to the bool1 variable. If we have bool2 equal to false, then false would be the other possible value for the boolean, and it would be assigned to the bool2 variable. So altogether we have only two possible value types, true or false. When is the boolean primary type being used? Well, typically in some kind of control flow in programs. So we might be talking about things such as logical expressions or relational expressions, if statements, while loops, things like that, where there is some kind of a condition which would be evaluated to either true or false, and then something would happen or not happen based on that result. There are two primitive data types in JavaScript, both of which refer to something that is empty. The first one of these is undefined. Probably the best way to think about undefined is of a variable which has been defined and which has been left blank. So you can think of an empty shelf, for example. But in fact, there is a value there, and the value there is undefined, but technically what the value would represent would be the fact that we have not yet placed what we intend to place at this location. So if we have the following line of code, let empt2 and then end there, so we are not assigning any value to this variable that we have just defined. And then if we call empt2, what would happen? Well, we would get a value back, we would get a result back, and the result would be undefined. So it turns out that there is a value associated with empt2, but it is just this default blank value that JavaScript uses to tell us that there is nothing there. So when we talk about an undefined primitive data type, it would have a single possible value that belongs to this data type, and the value would be undefined. So if we have a variable that has not been assigned yet, for example, its value would be undefined. Another place where you would very commonly come across this type of a value would be with functions. So all functions in JavaScript have to return a value, they have to return something. So we invoke them, we can send them some arguments, they're going to run some code inside of their bodies, but unless we have explicitly told the function to return something by including a return statement, what it would return would be this blank value. So be aware of that. The next data type in JavaScript that refers to a blank value is the null data type. Similarly to undefined, the null data type would have a single value associated with it. The value would be called null. And null would tend to represent a variable which has been left intentionally blank. So for example, if we have the following line of code, let empt1 equals to null. In this case, we would be assigning the null value to the empt1 variable. Notice we have done this intentionally. This was not done in the background by JavaScript for us. This was an intentional step. So the null primitive type, it does have a single possible value, null, and the value null would represent the intentional absence of a value in a variable or in an object property. So what is the difference between undefined and null? We have already discussed this, but let us make sure that we really understand. Imagine that we have two variables which we will define in a program. We have a line of code, let var1, and what we would do in this case is we would define an address in memory. It would be related to the var1 identifier, and then it would be assigned the undefined value to it, because we have not assigned anything else to that value. Undefined would go there by default. If we have a second line of code, let var2, exactly the same thing would happen. We would define a place in memory, the address that corresponds to the var2 identifier, and then we would place undefined there. Placement of undefined in both cases is done by default in the background by the JavaScript engine. If we want to add null, we have to do an additional step, and in this case we have to assign the value null to one of these variables. So if we would assign null to var2, for example, undefined would be replaced with null. So notice that in both cases we have a blank variable, but in the null case, the null is left there intentionally, whereas typically when we have something called undefined, it is either about to be assigned a new value, or it's just something that we are not interested in, like for example the value which is returned by a function which is otherwise not returning anything. The next two primitive data types are fairly specialized, so we would not be discussing them too much, but let us just introduce them so that we at least know that they're there. The first one is the symbol. And the symbol is used inside objects as a replacement for using a string as the key of a key value pair of a property of an object. Now we have not discussed objects yet, so don't worry if this is not making too much sense. But the key thing to remember is that a symbol is something that can be used if we absolutely want to make sure that the key that we are defining is unique. So no two symbols would ever be the same. Imagine that we have two lines of code. In both cases, we are defining constants, sim1 and sim2. And in both of these, we are adding the same value. So we are using a symbol object as a function. So we are adding the same thing to both objects. But yet, if we try to equate them, they are not equal. So what is happening in this case is that both of these symbols, even though they look the same, they are giving us unique values. And this is what symbols are used for. So they give us anonymous, unique values. They are generated by invoking the symbol function. And they allow us to have non-string keys which don't ever duplicate, making collisions of names impossible inside objects. The last primitive data type that we have not yet discussed is the BigInt. The BigInt, as the name suggests, deals with big integers. So, if you remember our discussion of the number data type, numbers run into problems if we have a large number of digits to deal with. Well, the BigInt doesn't have that problem, and it in fact allows an unlimited number of digits. But notice that it only works with integers. The way we define a BigInt number is by using a normal looking numerical literal with an n at the end. Notice how many digits this number has. In this case, we are looking at 100 digits taken from the number pi, but notice that we have removed the decimal point. BigInt numbers do not allow working with decimals. They require integers. So what we can do with this number type is represent mathematical integer values with no byte limitation. So we are not running out of space to record a number. And this number type is very useful if we are working with very large integer numbers. There is two ways to in fact define a BigInt number. One of them is what we just saw with adding an n to a number. The other one is by invoking the BigInt object as a function, where in this case we would place the number inside of the bracket. So a key thing to understand about BigInt is that they are very good at dealing with manipulations of large numbers. So in this case, we have in fact defined two BigInt numbers in two variables, bignum1 and bignum2. You would notice that the first number ends with 79. Now, if we had tried to make this addition using regular numbers, we would have gotten things most likely wrong because we ran out of digits. But in this case, we don't do that. And in fact, we get an answer which is valid. So notice that the last two numbers, 79 plus 1, gives us 80. Another thing to know about the BigInt number is that we cannot mix BigInt numbers with other value types. If we try to do and run the following line of code, where we would be adding 1 in the BigInt format plus 1 in the regular number format, we would in fact get an error. Let us go through the 7 primitive types again to make sure that we are all on the same page. So if we have a primitive value type, this can be the number, with the finite number representing the typical numbers that we think of when we think of numbers, But in addition to that, we had the positive and negative infinity, and then the strange not a number type, the none. In addition to that, we had the string with its double quote or single quote varieties, both of them generating a string value in memory. We had the boolean with the two possible values that it can have, the true and the false. We then had the two empty types in JavaScript, the null and the undefined, both of which have a single value associated with them. And then we had the two specialized types of primitive data types, the symbol and the BigInt. Now, out of the 7, it turns out that 5 of these can have something called a wrapper object available for them. What does that mean? It means that even though we define a primitive value type and, for example, store it in a variable, we can very easily convert the primitive into an object and then start applying methods to it. So, for example, if we have a single line of code, let string 1 equal to Tom. So now we have placed a string value, a primitive, into the string 1 variable. It turns out that, for example, we can very easily actually apply a method to that primitive value, which seems a bit strange because methods are not something which is associated with primitive values. Methods are something associated with objects. But in the background, JavaScript almost instantaneously and seamlessly can convert a primitive into an object if it's needed. And in this case, we do that. So if we run the toUppercase method, we can convert our string all to uppercase. And one thing that we can in fact do is we can use these objects, these wrapper objects, to in fact even generate our primitives out of. So one thing that we can do, for example, in this line of code, let string 2 equal to string object called as a function with John as an input. Well, in this case, we are actually generating a string. So this is a different way of generating a string value. So string 2 right now would have John as its value. And once again, we can quite easily call a method on this string 2 variable and then get all capital letters John in capitals. So these are the primitives. The next thing that we will talk about is objects and why are they so prevalent in the language.